Okay, yes, I want to welcome you all. Thank you for your attendance here today. The title that of our proposal is basically Illuminating AusLAMP, which is kind of a bit of a cheesy title, but the idea is really we want to understand what the finger of God really means. So we really want to see how that is done, and the method is relatively simple. The method is basically one that is already used in atmospheric sciences, where we go from cloud and aerosol physics to planetary waves to couple all the phenomena and try and understand the physics of the processes. And what we do is exactly the same. We go from the mineral dissolution at the sort of a minute to hour scale and nanometer level to the plate tectonic cycles and how that influences the behavior of our planet. And there are very important phenomena. Something as small as a hydrogen atom can fundamentally affect the electrical properties and the mechanical properties of our planet. So we believe that is actually indeed the reason why we have plate tectonics on Earth, but that's another topic. So the Illuminating AusLAMP project has a very ambitious timeline. It will start in January. It was actually scheduled to start in January next year. And we have two teams working together hand in hand. They're all two groups, one goal. We want to illuminate AusLAMP. And one of our collaborators here, the leader in Macquarie Uni is Juan Carlos Alfonso. He cannot be here today, but he sends his best greetings. And he's actually doing an equilibrium thermodynamic approach to understanding AusLAMP. What I will do here is basically focus more on the far from equilibrium. And putting this together, we have a better picture of the mechanics underneath. So we try to do this in a forward simulation before actually doing some concise laboratory experiments to try it from the physics point of view. So this is basically the AusLAMP project. Now, Macquarie's contribution here, you see, the idea is to link all these observables, heat transfer, gravity potential, Stokes flow, isostasy, dispersion curve, Maxwell equation for magnetic fluids, travel time, so the seismic images, all together in one and the same equilibrium thermodynamic approach. You might say, this is not possible. Well, it is very, very possible. Here is an illustration how it works. You crush up a piece of mantle rock, so it actually only works for the mantle, unfortunately, right now, so the crust is another story, but it works for the mantle. You crush up a piece of mantle rock, you do an XRD analysis, you have 45% of SiO2, etc., iron oxide, and then you do a Gibbs-free energy minimization, and that gives you for free all these physical parameters that you actually see there. So here, for instance, the density comes out automatically as a function of pressure and temperature. Note the temperature, we can go down right to the core, also in the pressure with these simulations. And we have compared these models with the Prem model, so we can actually predict elastic modulus, shear modulus, and thermal expansion coefficient. All these parameters can be actually predicted and compared with observations, and it works very well. It's surprisingly robust if the material is in equilibrium. Okay, so how do we link then seismic, MT, and other data? Well, this is the workflow of Alfonso. It should have said here, not in prep. It's actually published in 2016. I managed to change it in the last minute, but it's not. So it's actually now published. So we get the seismic images and say the VS. So we have an inversion for VS, and that is of course correlated with temperature. That can actually predict the temperature profile. And in the second step, you do then that actually is allowing us a 1D. In the second step, we can actually then link that up to this inversion where we actually put it all together under thermodynamic equilibrium assumption. And of course, what we can do then is predict all these beautiful structures. We get very nice 3D images of MgO, L23, etc., and the PDFs. So correlating with geoid, Bouguer anomaly, elevation, And so these are two different models, two different resolutions. And this is actually allowing us to say what is happening in terms of equilibrium thermodynamics. And there will be areas where equilibrium thermodynamics doesn't work. And these are the interesting areas. These are the areas where fluids go through the crust and the lithosphere and the mantle. And here we have some field images. And when these fluids go through the rock, they do something really strange that we are not familiar with in our current understanding. And this is a paper that we published in Weinberg and Viviakis and myself, where we have here, for instance, a migmatite from the Himalayas. You see it's densely folded, so sigma 1 is in this direction, but the melt, these leucosomes, are all extruded along the actual plane. So they're all extruded orthogonal to sigma 1. So they are not, this is not a tensile crack, this is an anti-plane crack. And it's not a crack in the first place because it's all melt, and it's actually a ductile instability that squeezes out these melts in these horizontal, in the vertical bands. Here's another illustration, there's another paper, the way we actually say ductile fracture is happening in these granites. So this is underneath the granite. This from the migmatite, it actually grows up. And you see a human here for scale. These are these melt bands that go through, and they're of course highly conductive. So they actually give us a conductivity anomaly. Obviously not in that single band, but if you have several bands parallel, and then you get 100-meter wide melt channels that propagate up to the surface. So this is how it works from the observation. But so here's another image, closer image of this beautiful migmatite fold, and along the actual plane the melt is being extruded. Now, can we detect deep fluids? Can deep fluids be the sources for MT? There's a lot of people who say, oh, it's graphite. So it's not fluids, it's something else. So can we actually uniquely identify that as fluids? Can we attribute them to the fluids? And how do these fluids in the first place go through something that is a solid rock? Okay, let's have a look at that. So we'll actually take a sample from the Red Bank shear zone here, so a nice beautiful granite sample from there, from the Runta. And then we stick it in the synchrotron. This was actually work done in 2009. So nowadays we can do that in the laboratory. And this is a shear zone, so on the top of the, this is a 16 centimeter tall sample. At the top you see it's actually phasing into the shear zone. Outside the material is in equilibrium, but here it's definitely not in equilibrium because it's shear. And when you scan these, these micro drills on this with 1 micron resolution, the red is a pore. You see that the pores are not connected here, so they're no amount. We can have very high conducting perturbations, small phases in there. They won't give you low conductivity, so you can pepper this. But in here, in this zone here in the center, they're all beautifully connected, and they give us a very high. They're just like wires going through the granites. Okay, so they give us high conductivity. So this is something that we can do now in the laboratory. And what's happening here? So the culprit here is probably this is another field observation, a mineral reaction where a solid goes over another solid and releases hydrogen and water. So it actually decomposes, a solid decomposes into a solid plus a fluid. This shear zone is entirely triggered by this reaction. So it's called a dissolution precipitation reaction. This direction of the reaction is endothermic. It requires work. If you don't work it, you don't get a reaction. And this is an exothermic. So if you release the work, well, it will actually drop back. So how can we study this? Now, here is an observation, for instance, from the northern Flinders ranges, where 2 parallel surveys, and you see these are basically these high conductors. Could they be fluids that are going through this dissolution precipitation reaction? So could we model it that way? Why do they get stuck at that ubiquitous 10 kilometers depth? So we have to answer that. We have to answer that question. So let's have a look at that. Now, how do we model this fluid transfer? We can't do it, of course, with equilibrium thermodynamics. This is a equilibrium thermodynamic phase diagram. We have to use far from equilibrium, and we unfortunately have to use some heavy mathematics that I'm going to hide here, because, I mean, you will fall asleep. So I'm just giving you a gimmick diagram here with a 1D shear zone. That's all we model in there. So we 1D shear zone, okay? And so we have an AB solid, so we don't know what kind of chemistry is in the first place. It goes into A solid plus B fluid. So let's do this. And here is another gimmicky diagram where we have two terms in the equation. One is a blast off, a thermal runaway instability, and the other one is actually capturing it by a chemical reaction, because the energy that we release here is captured in that in that chemical reaction, and that stops the blast off. So it pulls the rocket back to the Earth. Okay, so that's how it works. That's how the mathematics works. So I hope I have managed to illustrate some series of very complicated mathematical equations. When we do this, for instance, with serpentinite, okay, serpentinite, you know, serpentinite is is very rich in water. It dewaters at a certain temperature. This is what happens. So this is temperature axis, the pressure axis, and it goes very slowly here, and then suddenly it reaches the temperature for dewatering reaction, and bang, the water basically lubricates that fault zone, and there is an ETS event, a episodic tremor and slip event. And here you see our predicted episodic tremor and slip for the Cascadia compared to the observed GPS data downloaded from the web for Cascadia. So you can see it's actually like a heartbeat. Every 14 months there is a slip event. So it's a sort of it's basically stagnant, and then there's a slip event with these fluids that are released, and there's an overpressure here, 0.8 times the lithostatic, so it could potentially even crack the rocks. And you can see here tachycardia, so the heart is beating out of tune, but it's coming back into tune later on. So it's actually something else happened there, but it's actually really like the Earth has its heartbeat from these chemical reactions. So that's in 1D. Now how can we do it in 2D? 2D is a little bit tricky because this calculation is already done on the Regen supercomputer, and we have to do some tricks. So what we do, we just integrate over these oscillators. So we integrate over these various phases of the oscillator. You see it's actually long time, nothing happens, and bang, it actually creeps. There's a slip event. Bang, and when that happens, you find these sort of alignments. So this is quartz here, thin section analyzed. So when that happens, there's a sort of a creep fracture. This is K feldspar that's now precipitate. We did nanosims on this one. That's K feldspar that decorates the old fracture. So these are creep fractures, and we can use a method that has been invented in the 1982 in material sciences when they actually did this in sort of reactor vessels and so on, which are at 1300 degrees centigrade, so it's like a silica carbide, and you can see the diffusion creep and diffusion release of fluids into these fractures, and they creep along. So we can use the mathematics from there, and I'm successfully hiding again a couple of equations here through some cheesy diagrams. And so now we can apply that to the Australian case. So we know very well that in Australia we have Australia is colliding with Papua New Guinea since 10 million years, or around about 10 million years ago. So there's high stress in Australia. So that could be a driving force for these reactions. And we have little rock chips from the geodynamics well in the Cooper Basin, so that we can analyze. Okay, let's do that. Okay, now, if you recall well from there, the chemical reaction that we have there, we propose the same chemical reaction. There's hydrogen in there. Hydrogen has been released far from equilibrium. And if you recall very well, there was this blast out through 7-meter concrete, the blowout due to hydrogen embrittlement of the pipe. Nobody expected hydrogen in the fluids. Nobody expected the fluids in the first place down there at 5-kilometer steps. But there was hydrogen embrittlement because it was 35 megapascal overpressure, and when they shut in, the pipe shrinks, expands, and the stainless steel should have been chromium plated, and that basically killed the whole operation. So you're probably more aware of this than I am, because it's actually gone into Berg's grave, this whole project, unfortunately. It was a really ambitious project, and is it possible that this reaction is causing the observations? So let's have a look at this one. Okay, so this is then the top of the granite. So this is a televiewer image. So it's a 360-degree rotated view of the in the drill hole, and a shallow dipping sort of fault will be just seen as a very slight sinusoidal curve here. So you see it's a shallow dip around about only 10 degrees. And so question, is this thing here trigger a creep fracture that we illustrated earlier on? Here you see normal borehole breakout. You see it's under stress. So that's actually a function of happens after the well is being drilled. And but this one is a natural feature down there in the well. Okay, so is it a dissolution precipitation reaction? Is it causing these shallow wells? So we try this reaction, and then we take the topography, which is very well imaged to seismic images, so it's geologia habanero. The stress sigma maximum principal stress is pretty much oriented in this axis, and then we model so this would be the site of the habanero well, and we see that this reaction actually stops at exactly 230 degrees centigrade. So it's above the normal brittle ductile transition, but it's the activation temperature of this chemical reaction. So below, it's not activated, it just runs out of steam. So this is, we believe, the reason for these fluids to pond until the stress is high enough for another instability to take them up to the surface. Okay, so this is basically our interpretation of the habanero district. And the fluids, by the way, they are predicted to be a pegmatitic fluid, so they're a fantastic source for minerals. So if we harvest them, we might actually get our future mineral resources. So can we actually compare the results? Yes, we can compare. So you see, again, a borehole image here at the top of the granite. No, you just see the borehole breakout, but you see no fracture, nothing like that. At first fracture is 4,134 meters, and then we get more and more fractures as we go deeper. There's 3 fracture horizons. They're decorated by these stimulation events here that have been monitored by seismics. And so the key observations are here. Fractures only exist and can be stimulated above 230 degrees. You can't stimulate them in a shallow. You can see that the fracture, actually the top one that wants to go up, actually shallowly travels along the 230 degrees isotherm. It actually goes very shallow. Next observation. Fractures do not propagate into the sediments. They don't even propagate through the top of the granite. And they have in excess of 35 megapascal fluid overpressure. And I've already shown this overpressure reaction here. Fluids are equilibrated with the pegmatitic granite, so they are basically indeed a very strange chemistry. Lithium is enormous. Cesium, bromium, it's actually it's so-called billet fluid, which is actually in there. So it's a very nice mine source for the future. So we conclude carefully that fractures appear to be generated by the mineral dissolution reaction driven by geodynamic work. Okay, can we test that hypothesis further? Yes, we can go in the past. We can actually do this far from equilibrium buckling problem and look at conductors and signs for these anomalies here. So let's again look at the granite sample there, and let's have a look at a simulation through the entire Australian continent, 10,000 kilometers simulation. We cut out a section, and let's compress it in the past, and let's see whether we can actually generate the Arunta and the Musgraves through supercomputer simulations. Yes, we can. You can see here that it's actually here now a close-up view. The Musgraves and the redback shear zones are basically generated through these fluid self-organization from the bottom at 300 kilometers depths to the surface, so they are propagating up to the surface. So this is actually the direction that we're going right now, and the next steps would be that we go to apply this to Flinders case, Gawler case, and Northern Territory, and of course Macquarie Uni does the whole of the Australian continent, and then we actually try and actually focus on the TESA study. Thank you.